So hello guys, welcome back to our channel. So this is a hard problem. So it is not a moderate hard. So not a hard in name only. Okay, an actual legitimately difficult problem that requires you to master dynamic programming, design a precise size definition, and then when the naive DP isn't fast enough, so layer on the prefix some optimization to make it truly efficient. So this is the kind of problem that shows up in the top tier competitive programming contest and elite tech company interviews. So this is the problem, that is LeetCode 3130. So find all possible stable binary arrays 2. So today I am going to take you through every single piece of this problem. So what it is asking, why brute force collapses, and how to design the DP state from scratch. So why we need a prefix sum to cut the time from big O of n cube to n square, and every line of C++ solution explained individually. So three completely dry runs, so full complexity analysis and every common mistake you have seen people will make. So this is going to be through a one. So get your notebook. So let us go on to the session. So first let us see the problem statement first. So you are given a three positive integers, that is 0, 1 and limit. So a binary array is called to stable. Okay, a binary is called to stable if the number of occurrences of 0 in an array is exactly 0, the number of occurrences of 1 in the array is exactly 1. Okay, so if this all of these conditions, and one more thing, that is each subarray of array will with the size greater than the limit must contain both 0 and 1. Okay, so this is the condition. So here the all of the following three conditions should be satisfied simultaneously. So let us see if three conditions one more time. So the condition 1 is the number of occurrences of 0 in an array is exactly 0. So the parameter 0 tells us how many zeros the final array must contain. So in the next condition, so the number of occurrences of 1 in the array is exactly 1. So the parameter 1 tells us how many ones the final array must contain. So the next one is the condition 3. So each subarray of array with size that is strictly greater than the limit must contain both 0 and 1. So after that we have to return the total number of stable binary arrays. So that means we have to calculate through the subarrays within an array. So since the answer can be astronomically large, they have asked us to return it with the modulus operator of 10 power 9 plus 7. Okay, so let us look at this third condition, because these two you would get understand, but this will be some tricky. So the condition 3 is the main condition of this program, so it needs a careful attention. So let's unpack it precisely. So a subarray of array with size that is greater than the limit. So if we have a run of k zeros in a row, and k must be the most limit. So same for the ones. So for example, let me take some value here. So here, if for example I give the limit as 2. So after that there is 3 0. So this is the run of 3 zeros. So as you can see, it violates the condition because the subarray 0 0 0 has the size that is greater than the limit 2. For example, it is size 3. So 3 is greater than 2. Okay. So and all of them are same. It must contain 0 and as well as 1. So for example, all of them. So let us see one more example. Same with 0, 0, 1. So if I take this, so the total number of zeros, that is the total number of zeros is two zeros. Okay, so it is valid because the subarray of size is greater than 2, so that's all the same. Okay, so as we can see, the subarray should be like 0, 0 or 0, 1, like that. So it is greater than 3, but one more thing, it have both 0 and 1. Okay, it has still both 0 and 1. If it is the greater than limit, so as you can see, 3 is greater than 2. So but it have 0 and 1, so we don't need to do anything, it is valid. So if I take 0, 1, 1, so the subarray length is 3 and it is greater than 2, but it has still 0 and 1, so it is valid. I can say valid. So if I take triple 1 like this in array, so the subarray length is 3, so it is greater than 2. So but it still have all are same. So I can say it is violating the rule. Okay. So the size is greater than the limit. So and it have both 0 and 1, it is passes. Okay, if the size is less than 1, sorry, less than or equals to this limit, so we don't need to check that. So when this condition is passes, we have to check that it have both 0 as well as 1. So if it is, we can go into the subarray. So this stability constraint simply means there is no consecutive run of zeros or ones can be longer than the limit. Okay. So if it is limit is 2, there should be at most 2 consecutive zeros or 2 consecutive ones. Okay. So if the limit is 3, it can at most 3 consecutive zeros or 3 consecutive ones. But here the limit is 2. So the valid is 2 consecutive 1 or 2 consecutive zeros. So let us see the first example. So 1 0 1 1 and the limit is 2. So they have said the two possible stable binary arrays are 1 0 and 0 1. Okay. So let me remove this. So first we need an array with exactly 1 0 1 1. Okay, this is the 0 limit and this is the 1 limit. So we need exactly 1 0 and exactly 1 length, and the total length is 2 and the limit is 2. So since the limit is 2, any subarray size, for example, if any subarray size is greater than 2, would be need to have both digits. But our array is only size 2. So both possible arrays are 1 0. The maximum size is 1 0 and 0. So it should be differ. So the values are 0 and 1 different. So it is a valid. So the array of length is 2 with 1 0 and 1 1 can be possible of only these two outcomes. So no subarray length that is greater than 2 exists. So the both of these values are stable. So the answer is the total count, that is, so 2 is being printed. So the next one is 1 0 2 ones and the limit is 1. So as you can see, the array must have 1 0 and 2 ones. So the total length, I can say the total length is 3. I'll name this LEN. Okay, the total length is 3 and the limit is 1. So as I can say, the limit is nothing but the consecutive values. So it should be differ from each other value. So the values cannot be consecutive. It should be alternative. Okay. So for example, if we can say that this is the maximum consecutive digits it can hold. That is nothing but the length. So the length is 3 and the limit is 1. So for if you arrange all of them, so for the length 3, so I can say that for example 0, 1 and 1. Okay. So I can say that so the arrays are 0, 1 and 1. So after that 1, 0 and 1. So they have said 1, 1, sorry, 0, 1, 1 times of 0 and 2 times of 1. So 1 times of 0, 2 times of 1. So 1, 0 and 2 ones. So the possibilities are 0, 1, 1, 1, 0, 1, 1, 1, 0. So these are the possibilities. So now let us check that for the limit. So as you can see, the limit is one consecutive value. So there are two consecutive values in here. So that time it is invalid. So the count is still 0. So here it is changing and it is changing. So it is valid. So count will be incremented by 1. So here this both ones are consecutive ones. So that time it is a invalid value. So no two consecutive same digits should not be there. So the final answer is 1. So the output is 1. So the next one, that is 3 times of 0, 3 times of 1, and the maximum consecutive is 2. So as you can see that first there is 2 zeros. So they have given 3 zeros. So let me take 0, 0, 1, 0, 1 and 1. Like this I can take. So or else I can take in one more order, that is 0, 1, 0, 1, 0 and 1. Okay. So after that let us take one more thing. So in here it is 1, 1 and 0 and 1 and 0 and 0. So the limit is 2. So 2 consecutive values. So it is limited to consecutive values. So it can be alternating. It is the maximum limit. It should not be the same value. It can be less than or equal to the value. So 2 consecutive values, and alternating values, and 2 consecutive values. So the maximum run it can have is 2. So there are 2 zeros and 2 ones. So all of them are 1 and 0 alternating values, and 2 ones and 2 zeros here. So by alternating of these values, if you run this thing, so 1 less than 0 and limit is less than value. So the maximum total length of is 2000. So the limit is up to 1000. So this is what they have given us the constraint, that is 1 to limit can be 1000. So the total array length is 0 plus 1, which can be up to 2000. So here for it the total length is 6 they have given. So for doing this value it can exceed more than 2. So there are more values, as you can see here. These are the multiple permutations that this array can store. The final value is 14. So these are the few valid arrays I have written here. Okay, so here it is working perfectly. So now let us see why brute force fails for this problem. So before designing a optimal approach, okay, or optimal solution, let's ask what does a brute force look like and why does it fails. So a brute force approach would generate every possible arguments of zero zeros and one ones. So then check each one of the stability. So how many arrangements are there? Okay. So as you can see that if we do for every iteration, so that is 0 and as well as plus 1. So there are how many zeros and how many ones will be there. So and choose the 0, and if we do the binomial coefficient, so for example if I take 0 is 1000 and the 1 is also 1000, that's the maximum limit. Okay, so 0 is 1000, 1 is also 1000. So if you do the binomial coefficient, it is nothing but the c to the power of, that is 2000 and 1000. Okay, so the number has approximately 600 digits. So utterly it is impossible to enumerate. So what about the smarter recursive approach? So we could try to build an array position by position, tracking how many zeros and ones we have used and running invalid runs. So but without memorization, we revise the same subproblems exponentially many times. So the overlapping subproblems observation. So here's a key observation that we have to know that, so that it has points to the dynamic program. So we have placed some digits that we are position k in the array. So what determines all completions from this point onward? So there are three things. The first thing is how many zeros we still need to place for the permutation. So let us call it as I. So the next thing is how many ones we still need to place. So I will name it as J. Let us call it as J. So the third thing is what digit did we just place? For example, if we place something, we will name it. So what we place, that is K. Okay. So because that determines what run we might be extending. So nothing else is matters. So this specific arrangement of everything before position K does not affect the future valid arrangements. It will like a memory storing that we can use whenever we want. So only these three values do. So this is the classic overlapping subprogram structure that is dynamic programming is exploiting. So let us designing the DP state. So first, designing the DP state correctly is the entire challenge of this problem. So get the state right and the rest follows. So let's build it carefully. So first we have to define it. So for example, if I take, let me take the array as DP. So I'll give DP of 0, J and 1. So for example, I'll name it as I, J and K. So these three values. So within this, so the number of stable binary arrays using exactly I zeros and exactly J ones, and after that where the last digit is placed. That is k. So if k equals 0 means the last digit was 0. If k equals 1 means the last digit was 1. So that is the case. So first let us break down the base cases. So let's first we have to check the base case. So for example, if I is 0, okay, so that time DP is 0, so there is no zeros are remaining, okay. So we just need to place it with 1. So if my j is less than or equals to limit, so that is nothing but the number of ones. So a number of ones with no zeros is valid if and only if the j value is less than or equals to the limit of the maximum limit that is present here. Okay, so this is valid, and after that, if the same value, so with this same value is 0, and this value will become 1 because there is no 0 here. So here I is greater than limit. So we have to change the alternate value. So that's why it is 0. So j is, so it is not I, it is j. So j is greater than limit. So this one exceeds the limit. So it is a invalid. We don't need to check it. So for the third one, that is the dynamic programming, that where we should give the value that is 0, j, and the k value is 0. So it is 0 for all j, because it can't end with 0 if we have no zeros. Okay, so that's why we have given a the base condition. So same goes for j. For example, it is a base case for I is 0. So if j is 0, so that time the dp of I of 0 and 0 is 1 if the limit is less than or equals to the value. So same for that, if I is greater than limit, it is invalid. So we have changed the value to 0. So after that, for all I, it will become 0. So the recurrence, let us see the recurrence of this. So now the recurrence have 3 values, that is ij and k. So let's derive it for that dp of I, j, and let's take it as 0, that is k. So the array is ending with s0. So we are about to place the last 0 at the current position. So before this 0, we could have placed 1 or 0. So let's think about what came before this final 0. So there are few cases. So the first case is, there is, first let me break it down. So the first case or case A. So the digit before this digit 0 was a 1. Then we can freely come from the previous value, that is dynamic programming. We can simply change it to previous value, that is I minus 1 and j, and the previous value should be 1. Okay. So any array that is ending with 1 with I minus 1 zeros, okay, so and j of 1s, so that can be extended with s0. So for case B, so with this case B, the digit before 0 was also a 0. Previously we have seen the 0 before digit was 1, so now it is also 0. So then we can come from the previous value, that is the same dp of, so the previous value I minus 1 and j, but the previous value was 0. So the any array that is ending with 0 with I minus 1 zeros and j ones will have the value that is 0. So the dp of the current value, that is I j, with the previous value 0, I can say that it is equals to the value dp of the previous value j, and it is 1, and if I add it with the value that is present here with the value of 0 here instead of 1, so now it is not quite. So we must subtract the invalid cases where too many consecutive zeros are appear. So when does adding a 0 create the run too long? So if the previous limit elements are all zeros, so that means this value, that is the previous value with 0, so includes some arrays where the last limit positions are all 0. So if you add another 0 behind it, it would make the run limit plus extra one time of 0. So all of them would be invalid. So how many such arrays are there? So these are arrays where we have used exactly I minus 1 zeros. So the ending with 0 and j is 1 and the entire last limit element is the block is zeros. So this is equivalent to we had j 1 placed here there and the last limit positions are all zeros, which means the limit before the zeros we had a 1. So it is an invalid array that is equal to the value. So we can simply change the recurrence by the symmetric value for dp of 0 and 1. So the last element is 0, we have to calculate with the value of previous value, and if it is 1, we have to calculate with another value. So let us see it how to subtract with it. So for dp of, that means the dynamic programming, if the current value is 0, so we can simply check with the previous value I minus 1 j of the previous 0 plus the dp of I minus 1 j and the value 1. So we have to subtract this value with I greater than limit. If I value is greater than limit, so that time we have to subtract this value with dp of I minus 1 minus the maximum limit, because it will exceed the limit range of the value. So we subtract it with I minus 1 minus limit that is greater than or equals to 0. Okay, so if it is positive value, we will subtract it with this, or else if it goes to negative, we will just subtract with 0. Okay, and same goes for dp of value that is currently 1. So if it is 1, it is not I minus 1, it is simply j minus 1, and it is here also j minus 1. So now, as you can see, it is simply changing no other than I minus 1, that is previous 0 and previous 1. So for 1 you are checking with previous 1, for 0 you are checking with previous 0, that is I, and j here. So now we have to check that the j value is that is greater than limit. So if it is greater than the limit, so we have to subtract this value with j minus 1 minus limit. So if it is less than the value, we have simply subtract with 0. So why the subtraction term works here? So let me make absolutely sure we understand why we subtract this limit of j minus 1 minus limit. So this is the most subtle part. So when we compute the current value of the 0, so we are counting the array length I plus j. So that we use exactly I zeros, exactly j1, and it will be exactly end with 0. If we start with this value 0, it will always end with 0. So we add the dp, that is I minus 1 with j and 0, and the dp of, if you add these two values, the previous value of 0 and previous value of 1. So every valid this short array will be extended by extra 1 0. Okay. So, but some arrays in dp of the previous value, those value will be already in with the exact limit of 0. So when we extend it one more time, it will create the limit plus 1. So those are invalid for our counting. So we need to exclude them. So how many such arrays end with exactly run of limit zeros followed by nothing else? So that count is, using this formula, we'll remove that limitation, and because before the block limit is 0, there must be have at least a 1. So that is exactly this dp of I minus 1 minus limit will do. So after that it is j here and this is 1 here. So here it is dp of I here, j minus I minus 1. So for 1 we have removed with 1, and for 0 we have removed with 0. Okay. So here it will become 0 here, and here it is 1. So now let us optimize the problem from big O of n cube to the DP program big O of n squared with the prefix sum. So now we have our reference. So let me show you the naive implementation of this recurrence. Although correct, can still be too slow in some implementations. That is worth optimization, and how prefix sum are clean way to handle the entire family of those problems. So let us see the code line by line. Before that, let us see the basic approach of it, and let us see the dry run and the common mistakes people would do in this current problem. So we have a recurrence. So first let us see that. So but let me show you why the naive implementation of this recurrence, although correct, can still be too slow in some implementation. So first let us see what is the naive DP in the context. So in our recurrence, it is already in a constant per cell because each cell only have to look a constant number of previous computed cells. But I want to show you the relationship to the more version where prefix sum naturally emerges because it is a binary array. So you generalize the problem where the subtraction term is just one lookup. So consider the recurrence from the different angle. Okay. Here it is dp of the current value, that is ij0. If the current is 0, so it can be understood as the number of way to place I zeros ending with I plus j. So where the last run of the 0 is has the length 1 to 2 up to the limit, maximum of limit. So each of those corresponds to having placed at the 1 at a position. So that is I plus j minus the limit range, that is this running one. So and then the zeros. So it is nothing but the more formally we have written here. So sum of r from 1, and we have to subtract with the value in the minimum of I minus limit of this value. That is I minus 1 of limit of 1 for the 0 and 1 for, so if it is 0 we have to subtract with 1, if it is 1 we have to subtract with 0. Okay, so let us see the prefix sum trick. So the key observation here is the sum over the range of the DP. So let us move on to the problem statement. So first, so this is the main function they have given. So with this we have to write the code. So first I would like to implement this modulo. So all computations are done with this modulo. So this is the prime number frequently used in competitive programming because it keeps the value in the range while supporting the fast modular arithmetic. So we apply it in every addition and subtraction. So first it is 10 power of 9 plus 7. So first I'll make it as constant. So this is a constant value. I don't want to change it. So I'll name it as mod. So within it, if you give one A9, that is 10 to the power of 9 plus 7. Okay. So now we have stored it. So the next one is I want to find the total length that it can store. So for that, I initialize one variable named as n. So the total number of zeros from with the total number of 1. So that is the maximum it can store. So the stable arrays is using I zeros, j ones and last digit is k. So for doing that, we have to declare a vector, that is DB table declaration. So for that vector, so within that it will hold one more vector, and within that it will hold an array. So long, this long, this is the declaration part. So as you can see, so we declare three-dimensional structure with DP of I and j are arrays of two longs and DP of I, j, k. So this is an array of two longs and it have two values, that is 0 and 1. So that is the size of 2. So the dimensions are 0 plus 1 by 1 plus 1. So because the indices goes from 0 to 1 and 0 to 1 is the inclusive value. So that's why we have declared like this. So within this, next we have to name it as DP here. So after naming it as DP, we have to give the size that they have given us. Anyway, it should be 0 plus 1. Okay. So 0 plus 1 and it should have 0 as the value inside it. So 0, it is long, so 0 long and 0 long. I'll initialize it with 0 LN. Okay. So this is one size, and before that we have to store it with another vector value. So this will store for one vector value and we have to store it with another vector value. So 0 plus 1. So after that vector, so I'll give one space for better readability. So 0 plus 1. After that the next part, that is vector with hold another vector. So it is a 3D table structure. So array. So this array will have long values. Okay, the size is 2. So within this, we have to give the value, that is 1 plus 1 is the maximum size, and we have to initialize with the value of 0 LL and 0 LL. So vector which holds another array, and it is having the value of the DP here. So we have created one three-dimensional structure of the array. So where, let's see here, so vector which holds another vector with the array of long here with the size of 2. So within it, it will have the name is DP and the size is 0 plus 1. So within that, it will have another array, that is vector with array and long with the size of 2, which will store this size of 1 plus 1, and I will initialize with the value that is 0. So for long it is 0 LL. So let us do for the base cases we have previously seen. So we use long because it is intermediate value before taking the modulo, so that can exceed it range. So all entries initialize to 0 LL. So we use array of long 2 2, that is fixed size of 2. So instead of vector for the innermost dimension, it will avoid the heap allocation for every cell because there is only two outputs, that is 0 and 1. So a meaningful performance with when the table is large. So let us write the base cases. So the first is for in my I value is 1, I will initialize with 1, and I less than or equals to the number of 0, I plus plus. So if my DP of I value, okay, if I have zeros and 0 ones and the previous value is also 0, so that time it is equals to, we have to initialize the value. So first I'll check if I is less than or equals to limit. So if it is less than or equals to limit, I'll change the value to 1. If not, I'll change the value to 0. So another for loop. So in my j value is 1 and j less than or equals to the value that is 1 is the maximum value they have stored. So 1. So it is not 0. So it is simply 0. So 0 j plus plus. So getting the loop. So dp of, so the initial value is 0. The previous value should be 1. So after that, if j is less than or equals to limit. So if it is less than or equals to limit, I'll initialize with 1 or 0. So the same condition for both test cases. So then we have to fill up with the DP table. So the both base cases have been written. So now for in I is 1 and I is less than or equals to 0, I plus plus. So the second inner loop. So j is 1 and j less than or equals to 1, j plus plus. So first we have to check with the ending of value of 0. So I, j and the previous value is 0. So if it is ending with 0, so the dp value of, we have previously seen the formula, that is I minus 1 and j and 0. Okay, and we have to add it with the previous value of 1. So that is dp of I minus 1 j and 1. So after adding this, it should exceed the limit. So for that I am using modulus and mod. I will modulus this value with the mod value. So after that, if j is, first we are checking for 0, so it is I. So if my I is greater than the limit value, so that time my current value, that is dp of I j, and the previous value is 0. We are checking for the previous value 0. So now my dp of I j 0. Okay, so I j 0, that is the current value that we are storing, should be subtracted from the limit value. So dp of I minus 1 minus limit with j and 1. Okay, so after doing this, we have to add this value with mod and divide this value with mod. So after doing every subtraction and addition, we have to do calculations with the modulus value. Okay, so I minus 1 minus limit and j of 1 with adding modulus and dividing with modulus. So this is the condition that we are checking for if it is ending with 0. So what if it is ending with 1? So the dp. So before that, let us see this line, why it is written here. So first line, we accumulate all this table of ending arrays. So it is I minus 1, I minus 1 j. So whether they end with 0 or 1. So and it is extended by 1 or more 0. So this gives the array size with I plus j. So ending in 0 using I zeros and j ones, counting both valid and temporary over counted invalid ones. Okay, it will count the valid and temporary ones. So after that, this if limit. So if the subtraction part, if I is greater than limit, the array is counted in the dp of this value, that is I minus 1 minus limit. So it represents that we are adding this 0 and this already accumulated runoff limited 0. So we have to run off exactly limit plus 1 zeros. So we subtract those limit minus 1. So that time we get the correctness of this code. So we add here, that is mod. So we add mod before taking modulus because the subtraction can make the value negative due to modular arithmetic. So that time we have to check the positive value. So I am adding modulus value here. So it handles all the cases safely. So let us check for the symmetric value, that is the last value is 1 ending with 1. So it is I, it is j and it is 1. So if it is ends with the previous value of 1, so the same value, that is dp of dynamic programming of I j minus 1, and as we know we have to check with 0 and dynamic programming of this I. So j minus 1, after that the value 1. So it will be using modulus operator mod. So it is completely symmetric to the 0 case with roles of I and j is swapped, and
0 and 1 index will be swapped. So next for the if condition. So if j is greater than the limit, so if the j is greater than the limit, so we just dp of j 1, the previous value of 1, so the time, so dp of the current value I j 1 will be subtracted with the value of I here j minus 1 minus limit. Similar to this, so for here we have using this value in I, but here we are using it in j. So previously it was 1, but currently it is 0 here, and we have to add it mod for safer calculation and modulus with mod. So it is completely symmetric to 0 case. So the roles of I and j were swapped, and 0 and 1 indices are swapped. So we extend arrays ending with I comma j minus 1. So one more 1 will be incremented. So then we have to subtract for the invalid cases, and we will get the correct output. So now the final line of this code, that is getting out of this for loop, and we just need to return the value. So return dp of, so the 0 count and the 1 count with the previous value of 0 plus dp of the 0 count, the 1, the user given, and the value 1. So after adding these two, we just do modulus. So the final answer is the total number of valid arrays using exactly 0 zeros and 1 ones. So regardless of which digit is last, we just add 2 counts and take the modulo. So we are splitting this value and checking it. So now let's check to run it. So line number 25. So we need to give this. So let's run it. Okay, the test cases have been accepted. So the sample test cases being accepted. So let's dry run this program to check what is happening. So for 0, count is 1, and 1 count is also 1, and the limit is, so the expected output is also 2. Okay, so now we create a DP table, that is size of 2 cross 2. So that is the maximum limit it have, so we have to fill it. So first, let us check for the base cases. So DP and DP. So it should be 1, 0, and 0. So after that, 0, 1, 1, and 0, 0, 0. So now, first we have to check that 1 is less than or equals to 2. So it is true. So it is 1 and 0. This is the base condition for here. So first, let me copy this. Here also it is 1 less than or equals to 2, and dp of 0, 0, 1 here. 0, 0, 1. So it will be 0 because the condition is all of them are failed. So that time this value will become 0. So for this test cases, it is both are true. So that time it will be stored with the value 1. Okay. So now let us fill the value of I and j with 1. So initially I will be 1 and j will be 1. So now dp of 1, 1 and 0. So for this case, what we have to do, we have to just add the previous two values. So dp of 0, 1, 0. And after that, it will be added with dp of 1, 0, 1. So this value will contain the value of 1 and this will contain the value of 0. So 1 plus 0 will be 1. So now the I of 1 is greater than, so the I is greater than limit, so the I value is 1, so limit is 2. So if this condition is passes, that time we have to subtract the value. So 1 is less than 2, so it is still within the limit value, so there is no need for subtraction, so no need to subtract. So the value of dp of this current value, that is 110, will become the value 1. So after that, dp of 111. So now for the dp of 1, 0, 0, okay, it will be added with dp of 1, 0, 1. So in this case, this value is containing the value of this 110. So this 110 will contain is 100, sorry. So this 100 will contain the value of 1 and 101 will have the value of 0. So 1 plus 0 is 1. So let us check that j, so the current value of j is 1, is greater than limit. So the limit is 2. So it is false. So no need to subtract. So after that, we have to just answer it. So the final answer would be the dp of zeros, that is 1, 1, 0. So 1, 0, 1, 1, 1 with added with dp of 1, 1 and 1. So 1, 1, 1, 0 and it is for previous zeros and previous ones. So if you add the both value, so it is 1 plus 1. So we'll get 2 as the output. So we got 2 as the output here. So that's why this test cases is being passed. So let us see the complexity of this problem. So we fill the table size with 0 plus 1 and 1 plus 1. So each cell takes the time of big O of 1. So 2 additions. So at most 1 subtraction. So all of them are big O of 1. So I can say the total operations. So the time complexity is big O of, so the number of zeros is multiplied by number of 1. Okay. So with 0 and 1 both up to 1000. So the maximum speed, that is the maximum worst case, would be 10 power 6. So it is very fast comparably. So after that, the space complexity. So for the space complexity, it is big O of same 0 multiplied by 1. So we store the entire DP table which has 0 plus 1 and 1 plus 1. So there are two entries. So that is 0 multiplied by 1 space. So with the parameters up to 1000. So the max, this is about 2 million long longs. So roughly 16 megabytes. So well within LeetCode memory limits, can we optimize this space? So simply yes, because it will only depends on the row size. So it depends on row and column size. So we could potentially reduce by big O of minimum value of 0 to 1 with this rolling arrays. So but for this problem, this full table is fine and it is far cleaner to implement. So let us see the common mistakes and the edge cases. So most of them would forget to add this modulus when subtracting the value. So if you forget to do this, so what will happen? So if it gets to the arithmetic value of negative, so the negative modulo behavior is undefined in the C++. So that times it will produce some garbage value, so which should lead to error and the not answering correctly. So that is one of the biggest mistake in this problem most people do. So the next one is strong indexing for the subtraction. So we have to subtract with 0 of 1. So most of the people would confuse with 0 and 1, and that time the value of subtraction will be changed. So the next one is most people will forget to check for this base cases. So base cases are very important in dynamic programming. So make sure to initialize the cells with the value. So one more thing that people would do integer declaration instead of long. So the intermediate values before taking the modulo will exceed 2 power 31 minus 1. So for that use long throughout it. So that time it will not overflow within the value. We can just control it using long. And one more thing, that is people would forget to add from, that is 1 to 0, that is inclusive. But here people would do less than 1 iterations, that will get into the real problem here. So that's all for this today's slide. So first submit it and write our own solution in this LeetCode. So our solution is being accepted. So this is the problem description here, that is 3130. So LeetCode 3130. So just name it. So it is big O of 0 multiplied by 1. So same for the space complexity. So 0 multiplied by 1. So let's post our solution. So that was the real one. So let's bring it all together. So this is the LeetCode problem 3130. So it is a genuine hard. So it has three skills simultaneously. So defining a correct DP state and deriving a recurrence with the inclusion exclusion correction and understanding how the prefix sum is embedded to the recurrence of value to hit big O of n squared instead of big O of n cubed. So the time is big O of 0 times of 1 and the space is also big O of 0 times of 1. So both is optimal for this problem structure. So if this video is helped you, please like it, genuinely supports this channel. So subscribe so you don't miss the future hard problems walkthroughs, and drop a comment which part is taken first for you, the state definition, the recurrence or prefix and connection. So now stay with me for this announcement. So that's all for this today's live.